right, let's get into module 6 here then. So module 6 is about thermochemistry. Now, there's a good chance that you've probably seen bits and pieces of thermochemistry throughout your science and chemistry careers. But there's also a really good chance that you haven't seen most of this, or at least some of this, or at least parts of the details that we're going to go into here. So today we're going to start off slow. We're going to introduce some fundamental concepts. We're going to kind of set the groundwork and some of the stage for more of the calculations and stuff that's going to come over the next 4 days. So let's talk first and foremost about, well, what is thermochemistry? And so by definition, thermochemistry is the study of energy, including heat, that takes place and is exchanged during chemical transformations. Now, this kind of takes us back to something we saw in module number 1. We were able to break energy down into 2 big umbrella kind of categories. The potential energy, that is stored energy, that can be stored either as a matter of position, like gravitational energy, or charge, like electrostatic, or in the chemical makeup of the substance, either through bonds or through the composition of the nucleus and what holds that nucleus together. All of that is potential energy. It's stored energy. It's energy that is not currently being put into motion, but nonetheless still exists. Whereas kinetic energy is that energy of motion, the energy of movement. Now, we most often think of that in terms of mechanical energy. That is when objects are freely moving through space. But it can also be in terms of other kinds of motion, electromagnetic or electrical, the movement of an object through an electrical field or a magnetic field, the energy associated with the movement of electrons, electrical, or what we're tending to be most focused on in this unit, thermal energy, the energy of the movement of heat from one object to another. And so that's where our primary focus is going to be, is in this thermal energy here in this particular module. So some common energy units here that we might want to take a closer look at. Energy can be kind of described as being either just in terms of joules or in terms of calories. Now for joules, joules is kind of our universal energy unit. We find it used for all kinds of types of energy, whether it's mechanical energy or thermal energy or electrical energy. We can use joules to describe all of those. Calories, on the other hand, tend to be specifically used when it comes to heat. And where we find calories the most often are, calorie is kind of the imperial unit for energy. We see calories being used a lot for things here in the United States. What we need to understand is that while calories tend to be used more for thermal energy, especially here in the United States, joules are kind of used more universally. And so even though the description here talks about joules being used for types of energy changes that you can see, what we'll often find is that joules are also used commonly for describing heat transfer reactions as well. Now, by definition, a calorie is equal to the amount of energy needed to raise 1 gram of water by 1 degree Celsius. That is the textbook definition of a calorie according to pretty much any reference text that you will find. And so that provides for us a really good kind of standard to base our measurement on. But there are a couple of things that we need to also understand here. First of all, we need to understand that there is a difference between the calories that we are discussing here and what are called nutritional calories or kilocalories. And these are the kinds of calorie units that we tend to see on food labels. So, first of all, we need to recognize that there is a distinction there, that we do need to note that there's a difference. And the second thing that we want to notice is that there is a conversion between calories and joules. The conversion between calories and joules, there are 4.184 joules in every calorie. Now, how do I tell the difference between this common calorie and a nutritional calorie or a kilocalorie? It has to do with capitalization. Lowercase c calories are common calories. Uppercase or capital C calories, those are your nutritional calories. Again, where we see those kinds of things the most often are on food labels like this. So when I look at this nutritional label, which says that whatever it is that we are eating, 2/3 of a cup of it has 230 calories, 8 grams of fat, 37 grams of carbs, 3 grams of protein. Whatever that is, those 230 calories are capitalized, not just because they're the first word of the sentence, but also because they are referring to kilocalories as opposed to common calories. So that 230 calories that we're describing there is 230 kilocalories or 230,000 common calories. Now, the food label, how do we get to the 230? Well, that's based on a calculation. You know, each gram of fat takes 9 kilocalories to burn. Each gram of carbohydrate or protein takes only 4. And so if I take the grams of fat times 9 and add it to the carbohydrates times 4 and the protein times 4, that's how I get my calorie count there, usually rounded to the nearest 10, although sometimes it's rounded to the nearest 5. But with these values, I am able to convert one thing to another, and I can go in between one unit system and the other. There's one other really important distinction that we need to make here to kind of kick things off. And it's the relationship between energy and temperature. Now, we know, based on definition, temperature is a measurement of the average kinetic energy of the molecules of a substance. So if I measure an object to be -85 degrees, If I measure this object to be 85 degrees, I measure this other object to be 85 degrees. If I go down to the molecular level, each one of these objects is going to have molecules traveling at roughly the same speed because each of them has the same average kinetic energy. However, in spite of the fact that they have the same average kinetic energy, they have very different qualities of thermal energy. Because thermal energy is not just a function of temperature, it's also a function of quantity. You probably know this from experience. If I take a drop of hot water and it spills on my skin, yes, it hurts. But it dissipates pretty quickly because it was just a drop of water. If I were to take a pot of boiling water and pour that over my skin, that would hurt a lot more. Why? Because even though they're at the same temperature, the quantity of water makes a clear difference in terms of how much heat is being transferred to me. Whereas one drop of water, yes, it is going to transfer some energy to me, and that energy is going to cause me to feel pain. The fact that it's a small quantity does make a difference. And so as we're starting to evaluate the concept of heat and thermal energy, what we have to understand is that temperature is going to be a way to measure how heat is going to travel. It's going to allow us to predict when heat is going from one object to another and which direction that heat is going to flow. Temperature on its own is not going to be a measurement of the energy in the system, though. It's going to be a component of it, but it's not going to be the whole thing. And that's what we have to kind of keep in mind as we're going through and looking at and examining some of these examples that we're going to be exploring. Let's take a look at a couple of concepts here, just to review some of the preliminary things that we've been talking about. So which of these four definitions would be the best definition of thermochemistry? Give you about 30 seconds to respond. Okay, so we could definitely eliminate some of these options. So the study of matter during chemical changes, that's really not thermochemistry, that's just regular old chemistry. The study of electrons during chemical reactions, well, that's a branch of chemistry called electrochemistry. Electrochemistry has its heart in redox reactions, which is something we covered over the past couple of days here. So we're really between B and D. Does thermochemistry include heat or does it exclude heat? And the answer here is it definitely includes heat. And so no problems with that one. Let's take a look at a second review question. Does thermochemistry only consider energy changes during chemical reactions, or might it also consider energy changes during physical changes as well? So we can already eliminate B because we've already examined the fact that it's going to study chemical processing. So the question is it A or is it C, or does it depend on the situation? Give you another 15 seconds. Let me frame it this way. If I'm looking at a phase change, which is an example of a physical change, is heat being exchanged during a physical change? Absolutely. If I go to boil water, I'm going to need to add some heat to it because water's not going to boil just by slapping it down on the table here and saying, boil. It's not going to work. I have to include some heat. Heat has to go into it in some kind of way. So yes, there's going to be energy changes involved in physical reactions as well. So the ultimate answer here is A. Physical and chemical changes are able to be explored in this kind of way. All right, let's bring up another term here. The idea of a state function. A state function is a physical property where the value of that physical property does not depend on the path that we take to get there. So the key term in state functions is something called path independence. Now, what do I mean by path independence? Let me give you an analogy. Let's say that we wanted to climb this mountain. The distance in elevation from base camp to the top of that mountain is 2,500 feet. Our change in elevation would be considered a state function because the distance from here to here is 2,500 feet. It doesn't matter if we take hiker one's path and try to scale up the side of the mountain and go the most direct way possible, or if we take hiker two's path and we take the mountain trail and we work our way up to the top, but it's going to take us a lot longer in terms of total distance walked. A state function is path independent. So we're only concerned with what were we starting at and where are we ending. We're not concerned about how we got there. One thing that we will find in chemical reactions, and this will be especially true for those of you that move on to Gen Chem 2, is that there are a lot of different reaction pathways that allow us to get from point A to point B. In thermodynamic terms, we call those mechanisms. But we can think of these in the same way as we do these paths. Ultimately, what matters to us is the difference in our energies. So if we're looking at this from an energetic standpoint, at the top of the mountain, we have considerably higher potential energy than we did initially because gravitational position. We're at a higher gravitational position. What we're going to see here, we've got our first variable here. And that first variable, delta E, is how we're going to measure the change in internal energy. Now, why internal energy? Why not just energy? Well, because when we are exploring chemical systems, or really any system for that matter, we usually end up having to define the system itself and kind of pluck that system out from an overall understanding of everything that's around it. So we can bring in a couple of new terms here as well. What we're talking about are what we call the system and the surroundings. Energy transfers will always happen when energy moves from the system to the surroundings, or vice versa. Now, what is the system? What is the surroundings? Well, in chemical terms, the system simply refers to the chemical reaction that is taking place. So I've got my reactants, I've got my products, the overall chemical process that turns those reactants into products, that is my system. Everything else of relevance to that reaction that is not part of the atoms and molecules that make up the system is called the surroundings. So, real common example of this. We just went through a giant unit all about reactions taking place in water. In those kinds of reactions, precipitation reactions, titrations, gas forming reactions, the water, the solution, is not actually part of that reaction system. The water is the medium. It's where the reaction is taking place. So it's not actually participating in the reaction, it's encapsulating the reaction, it's surrounding the reaction, it's part of the surroundings. The reason we have to have this hyper focus on system versus surroundings is because without this focus, it becomes very difficult to track energy. Now, one more vocabulary term here for you to consider. When we look at the totality, the system and the surroundings together, what we get is a term referred to just simply as the universe. When we start looking at our thermodynamic laws, we'll start to understand why we use that term universe and why we actually care about that combination of system and surroundings at the same time. But for right now, what we want to think about and we want to kind of put our heads around is the idea of the system being just the chemical reaction taking place and the surroundings being everything else around it. Now, when it comes to systems, there are a couple of different kinds. 3 types of systems. I'll actually start here at the bottom because it's kind of the easiest one to understand. An open system. In an open system, matter and energy can freely move between the system and surroundings. Right now, you are sitting in an open system. Matter and energy are freely moving throughout this room. Any kind of open container also satisfies the requirement of being an open system. And because of this, open systems tend to be the ones we see the most often. They're the most common because they're the most easily acquired. All I need is some kind of a vessel, and that vessel doesn't have to be insulated. It doesn't have to even be closed. It can just be completely open to the environment. A closed system, on the other hand, restricts the movement of matter by putting a barrier in between the system and the surroundings that does not allow matter to penetrate it. However, that barrier, the vessel itself, is not sufficiently insulated to keep energy from moving in and out. Easy example to think of when it comes to a closed system is something like one of those water bottles that's got a screw-on lid. You know as well as I do that so long as the lid is closed, I can't drink out of it. So matter can't go in or out of that system. You know as well as I do that those water bottles, despite their construction, do get warm and cold. Put it in the refrigerator, it gets cold. Leave it out on the counter, it eventually gets to room temperature. Doesn't matter how much ice I put into that water bottle in the first place. It will eventually run out and heat up to whatever thermal equilibrium is existing. So it doesn't matter if I have just a simple Nalgene water bottle or one of the more expensive tumbler water bottles. Energy exchange is still going to happen in it. An isolated system is the most complex of systems because not only is it a closed system, it is also insulated. So I have a closed system that has sufficient insulation that energy does not easily transfer between system and surroundings either. So an isolated system has completely cut the system away from the surroundings. Best example we have of that is a really good thermos bottle, where so long as you keep the lid on and keep it capped, you know that that coffee that you put in there at 7 a.m. is still going to be hot sometime in the afternoon. You know, if you want to think about like one of those really advanced coolers like a Yeti or something like along those lines, those are pretty close as well. So long as they are shut, they do a pretty good job of keeping energy from transferring in and out, which is why they can keep ice for so long. So those are the three types of systems: open, free exchange of everything; closed, free exchange of energy but not matter; or isolated, no exchange of anything. Let's do a couple of review problems here. Here I have a pot of boiling water. What kind of system is this? Open, closed, or isolated? Get your answers in real quick here. Right away, we can throw out isolated. It's sitting here on a burner top. The burner is clearly having an effect on the water because it's boiling. So we know that energy is being transferred in and out. becomes a matter of, do you think that is open or closed? Well, it doesn't appear to have a lid on it. So the answer here is open. Let's look at another example. Here I've got a coffee cup. Open, closed, or isolated? So once again here, I think we can probably eliminate isolated from our options. Even the really good coffee cups kind of struggle with, especially these are paper, really struggle with keeping coffee warm for more than a matter of minutes. So what did we say? Okay, most of us are on the closed train. I always like this question because when I give this question, it usually sparks some kind of debate. Now, why did I mark this particular one as being open? I want you to look right there. If you view that hole in the top of the coffee cup lid as being a place where matter could be exchanged, as in I could drink out of it, I could put a stir stick in there, I could, funnel cream or whatever into the coffee cup through that little hole, then yes, it meets the criteria of being open. Now, if you want to get into a debate over, well, is it really open if I, put something over it, or if I, you could make those kinds of arguments. But as it's pictured right here, yeah, it's an open system. All right, let's wrap things up for today. I just want to talk briefly about sign conventions. So as we're moving into next week we are going to get into talking about the first law of thermodynamics. In particular, on Monday, we're going to talk about some different types of energy. We're going to look at heat energy, as well as work, and how they affect something called the first law of thermodynamics. But before we do any of that kind of discussion, we need to talk about signs, positive and negative in particular, because the sign convention for energy is a universal convention. So if we can understand what positive means broadly, we can apply it to every specific. If we understand what negative means broadly, we can assign it to every specific as well. Positive means an input of energy into the system. Energy is coming into the system in some kind of way. The overall energy of the system is increased. That's what it means when we have a positive sign. When we have a negative sign, that means that energy is leaving the system. It could be in the form of heat, it could be in the form of light, sound, whatever. But when energy leaves the system, we mark that as a negative change in energy. So energy in, positive, energy out, negative. Now, next week, we'll get into some more terms to kind of hone in on some more specifics there. That's what we're going to end for today. And so on your way out, Make sure that you answer this last question, the stoplight question, and I will see you on Monday. Have a great weekend.